Let me just quickly do a recap on how this course is structured. Chapter 2 was all about the construction of the derivative. And we spent that chapter breaking down what it really means and why it works. Right? And this is why most of the chapter was about limits, because that's what's underneath the hood of a derivative. If you'll indulge me with the analogy between a derivative and a car, which I find is actually helpful when you're thinking about the roadmap that takes you through this course. Because chapter 1 was really just review from high school. Chapter 2 is where the course started. But chapter 3, now that we had the derivative developed, we focused on techniques of actually finding derivatives. Right? That's why chapter 3 is called Techniques of Differentiation. And there's lots of techniques, and we don't even get into all of them in this course. Unfortunately, we just don't have time. And if you continue the analogy between the derivative and a car, chapter 3 is essentially where you learn how to drive. Now, chapter 4 is going to be about where do you want to go. Now that you know how to drive the car, where are you going to drive to? And in our case, we're going to look at two main applications, optimization and curve sketching. And we've already looked at one major application at the end of chapter 3, and that was just the previous section related to rates. Right, but we're going to look at two more main applications, optimization and curve sketching. And we're going to start with the theoretical fundamentals of optimization in section 4.1. Really, just start by talking about what it means to optimize something. Well, it just means to find its maximum and minimum values, and that's what section 4.1 is about. And then we'll get to some real-life applications of this concept near the end of the chapter. Okay, so let's start with the fundamentals. So we'll start with the function f that's defined on some domain D. And what do we mean by the maximum and the minimum? Well, it depends on the context. And that's what we're going to clarify now. So we say that f of c, and I'm about to say under what circumstances f of c is called the absolute maximum of f. And the reason I've written it down in this form, f of c, is I want to make it extra clear that we're talking about not just a number, but because it is a number, but it's a number that appears as an output value from the function f for some input value c. So under what circumstances is f of c the absolute maximum of f? Well, roughly speaking, it means that it's the biggest value you can get from f as an output value. So how do you say that mathematically? We say it like this. If f of c is greater than or equal to f of x for every other choice of x. Right? There's no other value x that will now give you a bigger output value than f of c. So that's how we'll word this. So to finish the sentence, we'll say f of c is greater than or equal to f of x for every x in D. Okay, and then for the corresponding idea on the other end of the spectrum, you've got the definition of the absolute minimum of a function. So an output value, f of c, from the function f, is the absolute minimum of f. Well, we'll use the same definition, except it's now got to be the smallest value, not the largest. Right? So you can use the same definition, but just flip the inequality sign. So we'll say f of c is less than or equal to f of x for every x in D. Okay, so those are the definitions of the absolute maximum and the absolute minimum of a function f. And the way we define it by just telling you under what circumstances something of this form is either the absolute maximum or the absolute minimum of f, and that's enough to define it. But there's also ideas of local maximums and local minimums. So let's start with a local minimum. What does it mean for f of c to be a local minimum? So this is a weaker definition than absolute minimum. So the local minimum of a function is really just a minimum that happens on maybe a narrower range of x values. So here's how we'll say it. F of c is a local minimum of f if f of c is less than or equal to f of x. But we're not going to require this inequality to be true for every x in the domain of D, because then that would be an absolute minimum. So all we're going to do instead is just require this to be true for every x near the point C. And remember what that word near means. If I say that a statement is true for every x near C, all I mean is there's some open interval that contains C such that this statement is true for every x inside that interval. Now I might have to take a very narrow interval. I might really have to zoom in around the point C in order to be able to accomplish that. But as long as it's possible to be done, no matter how small that window ends up having to be, then it's fair to say that f of c is less than or equal to f of x for every x near c. And we'll do the same thing for a local maximum. So f of c is a local maximum of the function f if f of c is greater than or equal to f of x for every x near c. All right, so let's look at a picture of what these definitions actually mean. The picture would look like this. So let's draw something like this. I'll just draw a curve that kind of has some peaks and valleys. And, well, let's look for the absolute maximum first. I'm not even going to draw the x-axis and the y-axis here because they kind of get in the way of the pictures. But imagine there's an x-axis somewhere and a y-axis somewhere. You can just fill that in on your own. But here would be the absolute maximum. It's the absolute peak of the function. It doesn't ever go any higher than that, or at least it doesn't look like it does. Unless, if I continue the drawing, maybe it does over here. But let's assume that it just kind of levels out and doesn't go any higher than that. So this would be our absolute maximum. I'll just say absolute max for short. And then the absolute minimum is right down here. This is the absolute lowest point that the function ever hits. This is the absolute min. Okay, what about the idea of a local maximum or a local minimum? Well, here's a local max. Right, that's an example of a local maximum. Because if I restrict my attention to just maybe this area of the graph and I forget about everything else, or maybe I'm just zoomed in, and maybe I'm looking at this graph on a piece of software and I zoom in so that all I can really see is a box around this point and I don't even see anything else, well then I would think this is the absolute maximum value of the function. And because I can zoom in enough to make that the case, that's what it means for this to be a local max. So I'll just put some arrows here. Now, what about a local minimum? Well, it looks like there's maybe one around here somewhere. This looks like that's a local minimum for the function. Because if I just zoom in around here, it looks like this is the smallest value that the function attains. So that's why it's a local minimum. Okay, and if you're being technical, this is also a local minimum. Because if I zoom in around this point, I'm going to think that this is the absolute minimum. It turns out I'm right in that case, but it's still a local minimum as well. So if you're a local minimum, if you're an absolute minimum, you're automatically going to be a local minimum as well. Similarly with maxes, the absolute max is automatically a local max as well, but the reverse is not true. Okay, so some terminology. When you're referring to absolute maximums and minimums, you'll just use the phrase absolute extrema quite often. So absolute extrema just refers to things like the absolute max and the absolute min. But then local extrema just refers to local maxes and local mins. So you're talking about things like this. And technically these as well, right? Because they're also technically local extrema because they're absolute extrema. So an absolute maximum is automatically a local max. An absolute min is automatically a local min. So therefore, absolute extrema are automatically local extrema as well. So this local extrema includes both. Okay, so that's the idea of local maxes and local minimums. So if you're trying to optimize a function, really it means you're looking for those. You're looking for the absolute extrema and the local extrema. Or sometimes you might be looking for just the absolute extrema. It depends on the context. But quite often local extremas are very interesting as well because they tell you information about how the curve behaves. Okay, and I'm going to finish this page off with a couple of theorems that we're going to use in this section. The first one is called the extreme value theorem. And what it does is it gives you sufficient conditions on which it can be guaranteed that a function has absolute extrema. And it turns out that the conditions are not that strict. It just says the following. This is what the theorem says. If you have a function f that's continuous and defined on a closed interval a to b, and it could be defined outside of this interval as well, but for the purposes of this theorem, we're going to just restrict the domain of the function to only this closed interval, and we're going to absolutely ignore everything that happens outside of there. So if you have a function f that's continuous and defined on a closed interval a to b, then the extreme value theorem tells you that f is going to for sure have an absolute max on that interval and an absolute minimum on that interval. Okay, so that's the first theorem. So that's good. That means if you have that setting, it makes sense to actually invest your time and energy actually looking for the absolute max and the absolute min. So that's one of the strengths of this theorem, is that it tells you under certain circumstances when you're definitely not wasting your time looking for a max or a min. Like for example, think of the standard parabola that starts the standard parabola with a vertex centered at the origin, y equals x squared. Imagine what that looks like, right? I can draw a picture over here. If I draw this picture, y equals x squared, it looks something like this. I'm not going to label anything because it's just a rough sketch. That has a minimum, but it doesn't have a maximum. Not unless you restrict yourself to a closed interval. If I chop it off on either end here, and maybe I call this a and I call this b, well then that's going to change things, because then the function will be cut off, and then there will be a definitive maximum that function attains. But as it stands, if I just consider this function over the entire real line, it just goes up forever on both ends. So it never actually hits a maximum, even though it does have a minimum at 0. So that's an example of why it's important that your function not only be continuous, but it has to be defined on a closed interval. Okay, so that's the first theorem. And the second theorem, which is called Fermat's theorem, says the following. Let's say you've got a function that has a local maximum or a local minimum. So you've already found a local extrema. Imagine that. And you've found the location at which it occurs, some value c. Well, this theorem, Fermat's theorem, just tells you that if the derivative of that function exists at the point c, then the only value it can take is 0. Okay, so that's what Fermat's theorem says. And really, there's a consequence of that, which I'll get into after we draw a picture. So at the beginning of the next page, I'm going to draw a picture which kind of illustrates what this theorem is actually telling you.